time. So in this case, we're measuring the position of a particle in the wave at a fixed point of the wave. So essentially we take out one bit of the wave. We can see that we have a wave moving to the right over here. But if we want to graph a position over time, then we need to pick just one particle in the middle and draw a graph of how it moves, right? So we can see that it's going to be moving up and then down over time. So this isn't exactly the same as graphing over position, because we don't see the entire shape of the wave as it moves from left to right. What we do see is the movement of how the individual particles of the wave move, which can also be useful. So the graph will represent the motion of a single particle and not of the wave as a whole. It'll show how the wave changes over time, which means that we can measure certain properties of the wave related to time. Can you think of any properties like that? Plot the voltage against time of a wave with a frequency of 4 Hz and an amplitude of 3 volts. So in this case, we're measuring the amplitude not in centimeters, but in volts, which doesn't actually make anything that much harder, don't worry. Now we're plotting the voltage versus time, which means that we look at a fixed point of the wave and show how it varies up and down over time. So if it has 4 Hz, that means that in 1 second, four whole wavelengths will pass through the particular point that we're looking at. So our graph will look something like this. We can see that in 0.5 seconds, we have 2 whole wavelengths. That means that in 1 whole second, we'll have 4 whole wavelengths. The other way we can look at this is by finding the period of the wave, which will be 1/4, 0.25. We can see that if we look at the period of the wave here, which will be 1 whole wavelength, then it's, as we would expect, 0.25. Our amplitude has to be 3 volts, which means that our y-axis will be plotting voltage. And once again, we can see that it will go from 0 all the way up to 3 and all the way down to -3.